Hello. Today, I'd like to present a project focused on a fundamental yet powerful algorithm, the majority element algorithm. So, it answers a simple but important question. Does one value appear more than half the time in a dataset? This kind of analysis is crucial in many real-world situations where we need to detect a dominant behavior, a signal, or a pattern quickly and reliably. So, what this project covers? In this notebook, we are going to explore two versions of the algorithm, some real-world use cases that I'm going to present right after this, and finally, we are going to do some comparison and analysis of the two algorithms, also try them with different dataset sizes. So, for the first real-world use cases, first we have data cleaning. In noisy environments like sensor data or pixel streams, we can apply this algorithm to small data windows in order to preserve the dominant values and remove outliers. For example, here you have a stream value that are really close to 22, but we can see that we got also a 55 that is clearly an anomaly, and we also call this a noise. So thanks to applying the algorithm, we are going to see that the main value is 22, and we are going to ignore this value here. Another example is DDoS attack. So in cybersecurity, we can detect abnormal behavior by identifying whether a single IP address is dominating the traffic in a short time window. For example, if one IP sends more than half of the requests during one single second, it's likely a bot or part of an attack. So for example, here, for 10,000 HTTP requests collected, we can see that 6.7 thousand are originating from the same IP address, which we will be able to flag as a bot and ignore and eventually block to prevent the cyber attack. Lastly, we have the personalized recommendation system. So on platforms like YouTube, Netflix, or Spotify, we can use the logic seen before to detect a user's recent dominant interest. So for example, in video games or a documentary, then we can adjust its recommendation in real time to follow the trend. So to do a little summary of the benefits, we have no learning phase required. We have a simple implementation with a highly robust algorithm because the algorithm is quite simple and only do one thing. It doesn't try to do a lot of things. And we have also strong performance, but we will see this in the next part. Hello guys, we just did the first round for the presidential election today. We have 4 different candidates. So I'm going to use this naive algorithm to find if someone got the majority of the votes during the first round. Let's go. Wait, guys. Why is it taking so long?
That's because you're using the naive approach. You should use the divide and conquer one. It's much faster. Let me show you why.
So we're gonna first analyze the complexity time of the naive approach. By taking a quick look on the naive approach, we can see that we have two loops which are gonna iterate through each of the elements of the array having a size n. We can quickly deduce that the time complexity of this approach is O(n) squared. Since we're gonna go in the first loop through every element of the array, and in the second loop we'll also go through every element of the array. Then we're going to proceed to analyze the time complexity of the divide and conquer approach for finding the majority element. So let's first focus on the recursive helper function. So each recursive call splits the problem into two halves, and then we perform a linear scan to count and compare the results. So the recurrence relation modeling this process is this: Tn equals to 2t of n divided by 2 plus 2n, where 2t of n divided by 2 represents the two recursive calls, and the 2n is the cost of counting and comparing the elements after the after the recursion. Then we can check that this 2n, which is equals to our fn of this form here, belongs to the complexity On. We can then determine the g, which is equals to 1. So we identify a and b, which are 2 and 2. We're gonna calculate lambda, which is log b of a, which then is gonna be log 2 of 2, which is equal to 1. And then we can see that G equals to lambda, which is the case 2 of the master theorem, and we can see that the time complexity of the helper function is n log n. So in the whole algorithm there is a last step, which is here, where we can call the final count time, and we can see that is of complexity O(n). Since the count here is gonna go through each element of the array of size n and check if the value equals to the candidate. So by comparing the two complexity times, we can conclude that the time complexity of the divide and conquer approach is n log n, which is way lower than n squared of the naive approach. That's why it's a much faster algorithm.
How do you know this algorithm is valid?
Oh, that's a really good question. That's why we did for you the proof of the correctness of this algorithm. Let me introduce you to this proof. Alright, so now let's dive into the proof of this algorithm. So I'm gonna prove you that the majority divide and conquer algorithm, which find the majority element in an array, is both correct and always terminates. First, we want to be sure that this algorithm always stops no matter the inputs. Because the input size is strictly decreasing at each step, we're guaranteed to reach that base case in a finite number of steps. And we can prove this by induction. The base case here, for size 1, the function returns immediately and then it stops. And the inductive steps, if the algorithm stops for an array of size n, then for size n plus 1 it breaks into two size n or smaller problems. Those both stop by the induction hypothesis, so the full call does as well. So by this proof we show that the algorithm always terminates, right? And now let's get into the correctness. We want to prove that if there is a majority element, it will find it, and if there is no, it will return none. Let's prove this again by induction on the array size. The base case here, if the array has only one element, that element is clearly the majority, and it's return, right? So it's correct. On the inductive steps, we assume that the algorithm works for any array of size n or less. Now we take an array of size n plus 1. The algorithm will split it into two halves and recursively find the majority in each half. So then we compare the two results. If both halves agree, we return to that value, it's the majority. If they're different, we count how many times each appears in the full array and return the one that appears the most. Finally, we do a last check. If the chosen candidate appears more than half the time in the original array, it's returned. Otherwise, we return none. So no matter what, the algorithm returns the correct majority if it exists, and it returns nothing otherwise. So to conclude, the majority divide and conquer algorithm is both correct and efficient, and ready to handle large real-world datasets. So yeah, you should definitely try this algorithm in your election.
Oh, okay, so I see this algorithm might work. Okay, I will just try it. Let's go. I have the new algorithm. I will try to compute if we have the majority right now. Let's go. Oh my god, guys, look! It only took 0.2 seconds to have the result. And so now we can deduce that nobody got the majority during the first round of this presidential election. So now we have to go into the second round. So I will run once again my algorithm and try to look who is the big winner of the election. Let's go, guys. Oh no, guys, we might have the same problem as just before. It's taking way too long. We don't have time for this.
I noticed that you're using the naive algorithm again to check for a majority. You don't remember what we said just before? It works, but the complexity is n squared. So it's really too slow for large datasets. You should try the divide and conquer version again. You will get the same result and it will be much faster.
Oh my, you may be right. Okay, let's choose the divide and conquer approach once again. So I have this algorithm. I hope it will work just fine. Oh, wow, look at this, guys, so fast. It only took 0.03 seconds. And now we know that the big winner of the election is candidate number 2. Congratulations! So now we are going to do an experimental comparison of the two majority element algorithms that we studied So first, for the naive algorithm, we saw that the complexity was of n squared, and for the divide and conquer algorithm, we saw that it was of n log of n. For our setup, we are going to choose different sizes of array and compare the time for each algorithm to compute and find the majority element in each of the array. So here's the Python code. So we have here the majority naive and here the majority divide and conquer. And we wrote a little algorithm that allow us to generate an array with always a majority. And this is a little function that just allow us to quickly compute and compare the result. So we are going now to try for different sizes the algorithm and see what we got. So here we can see for a size of 10, the naive algorithm finds the result a little bit faster than the divide and conquer. But for the size of 1,000 and 10,000, we can see that the difference start to get more and more big. We can see also on this array that the time is a lot faster when n became bigger. So for the performance analysis, for small inputs, we can see that the algorithm, the naive algorithm, is a little bit faster. But after n became, let's say, bigger than 20 or 30, the divide and conquer is always a lot faster. And as n became more and more big, the difference became more and more noticeable. So the naive algorithm is of complexity n squared, which is only acceptable for really small array, and in much application will not find any uses. Meanwhile, the divide and conquer will be really efficient for really big array, which will be much more interesting depending on the application.